All right, we're going to take a look at the first free response question from the homework for 10.10. And I like this question because it works in a couple different ideas, some of which are on the ABA exam, some of which are on the BC exam, because this is from a BC exam free response question. And involves Taylor polynomials in a way that we don't regularly see when the FRQs ask about Taylor polynomials and series stuff. All right, let's go ahead and get started. So we have a function. It is twice differentiable for x is greater than 0. We know f of 1 is 15. Probably should make a note of that. That probably sounds like it'll be important somewhere along the way. F of 1 is 15, and f double prime of 1 is 20. We have that information. Values of f prime, the derivative, are given up here for selected values of x. All right. A, write an equation for the line tangent to the graph of f at x equals 1 and use it to approximate f of 1.4. All right, let's see. Tangent line approximation. We know how to do that. We need a point. Our point at x equals 1. So let's see. F of 1 is what we need, because we want the tangent line to f. So f of 1 is 15. So our point, we have 1 comma 15. That's from up here, right? We also need our slope at 1. So we need f prime at 1. F prime at 1 looks like it is 8. That's up in our table, right? So that means our slope-intercept form is y minus 15 equals m, that's 8, x minus x1. So there is our tangent line approximation. All right, now we need to use this to approximate f of 1.4. So f of 1.4 is what we want to approximate. It is going to be approximately, I want to add 15 to the right-hand side. It's going to be approximately 8 times 1.4 minus 1 plus 15, right? All I'm going to do is solve for the y value in my tangent line. I'm going to move 15 to this side, plug in 1.4 for my x value, and I can leave my answer like this, all right? 8 times 1.4 minus 1 plus 15 is my answer. No need to simplify. It does come down to 18.2. All right. So that would be part A, tangent line approximation. Not too bad. Not too bad. Definitely a skill you need to have in your back pocket that you can expect. Okay. Let's take a look at the next part. Part B, what does it say? Oh, I should have said, if I go back for a second, scoring-wise, you would get 1 point for your tangent line down here, all right? And then 1 point for your approximation up here. Whether or not you left it unsimplified, which is what I recommend doing, you have to simplify down correctly if you're going to get that second point. Otherwise, you get 1 point for this and 1 point for just your expression for the actual value or the actual value. 2 points total. All right. Our next part, part B. Use a midpoint Riemann sum with 2 subintervals. Okay, midpoint Riemann sum, 2 subintervals of equal length, and the values from the table above to approximate the integral from 1 to 1.4 of f prime of x dx. Okay, let's do that first. The integral from 1 to 1.4 of f prime of x dx. I'm going to use a midpoint approximation for this function. I want the area underneath this function, which is what I have up here in my table. So my midpoint approximation. All right, we want 2 subintervals, and we're going from x is 1 to x is 1.4. So I'm going all the way across this table. So what is my interval? Well, my first interval, if I need 2 intervals of equal length, my first interval would be right there. So my delta x, because I need that, my delta x, change in my x value is going to be 0.2. Because I'm going to go from 1 to 1.2. That's the width of my rectangle. And then 1.2 to 1.4. That's going to be the width of my next rectangle. They're equal delta x's, because that's what we're asked for in the problem. So for my first rectangle, the base of my rectangle is 0.2. I'm going to multiply it by my midpoint height, which is 10. I want to add on to it the area of my next rectangle. The delta x is 0.2. And then my midpoint height for my next rectangle, the height of my rectangle is 13. Okay, there we go. That is my midpoint Riemann sum approximation. You can leave it like that, all right? Remember, don't simplify if you can help it. For those of you who are feeling the urge, I discourage you, but it is 4.6. Okay. So what do we do from there? Let's keep reading our problem. Use the approximation to estimate the value of f of 1.4. This is the original function, right? I want to estimate the original function, 1.4. Show the computation that would lead to your answer. Okay, I'm going from a derivative value to an original value. I would know then that in general, for some function f of a, this is my fundamental theorem of calculus, right? F of a at some value is going to be the derivative. Oh, sorry, why did I say that? It's going to be the function at the starting value. And my starting value that I'm working at here is 1. It's going to be f of 1 plus the integral from 1 until a of the derivative. This is our sort of final amount formula that we need to know. The initial amount of our function we're measuring plus the integral from 1, I chose 1 in this case because that's where we're starting here, from 1 to a, our ending value of the derivative. I know what a is, though. In this specific situation, I want f of 1.4, which is going to be f of 1, my starting f value, plus the integral from 1 to 1.4 of f prime of x dx. And I know a lot of these values. F of 1, I already had up here in my problem, is 15. So it's going to be 15 plus my integral from 1 to 1.4 of f prime x dx. It said use this integral to approximate the value. So I'm going to use the value I just found up here, which is 4.6. And I'm going to say that 19.6, I guess this should be, in this case, this is approximation. So I'm going to change this sign over here. F of 1.4 then will be approximately f of 1, which is 15, my initial value, plus the integral of my derivative across my interval from 1 to 1.4. So I found that that was 4.6, so add them together should give me 19.6 as my approximated value. So you got 1 point for your midpoint Riemann sum, which was right here. You did not need to simplify. You got 1 point for recognizing you need to use the fundamental theorem of calculus down here. This guy right here, recognizing f of 1 plus the integral from 1 to 1.4 of f prime of x dx, and then 1 point for your final answer. You did not need to simplify it. You could have left it unsimplified. All right, let's keep on moving. So that's 3 points. Midpoint, fundamental theorem of calculus equation, final answer. Okay, part C. Part C says use Euler's method, starting at x equals 1 with 2 steps of equal size, to approximate f of 1.4, show the computation that lead to your answer. Euler's method. This is one of those we got to remember. I like to do it in sort of this table format. So I need to know my point. I need to know my delta x. I need to know my I need to know my dy dx. dy dx. That y got a little ugly looking. dy dx. I need to know dy dx times my delta x, because that'll give me the change in the y value. And then I need to know my final point over here. So x plus delta x, comma, y plus delta y. How much did my y value change? All right. So my starting point when x is 1, my starting point on my curve is 1, comma 15. Right? That's the point I'm given up here in the problem. F of 1 is 15. What is my delta x in this case? We want 2 steps of equal size, so that means delta x is going to be 0.2. dy dx then. dy dx here at 1, I always want to start the derivative. I need the derivative at the point I'm working at. The point I'm working at from my table up here is 8. And then I need to multiply the derivative that I got by how much my x value is going to change. So 8 times 0.2, 8 times 0.2, all right? That's going to be 1.6, right? 1.6. This is our delta y. You can think of it that way. Is our delta y. How much did our y value change? 1.6. So my new point is going to be x plus delta x. That's 1 plus 1.2, so 1.2, comma y plus delta y. Y was 15 plus delta y is 1.6, so this will give me 16.6. That's the new point that I'm going to work from here. So my new point, 1.2, comma 16.6. My delta x is still 0.2 because I'm moving over. I'm trying to get to 1.4, so I start at 1, I add 0.2, and then I add 0.2 again to get to 1.4. So let's see, my dy dx at 1.2. My dy dx at 1.2 is 12 from the table. Then I take my 12, I multiply by how far I moved over. So I need 12 times 0.2. That'll give me 2.4. 2.4 is my delta y. So then I add my x value plus my delta x to give me 1.4, comma, my y value plus my delta y will take me to 19. All right. So I just did my 2 steps, and what do I find? I find my approximation, my Euler's approximation then, for f of 1.4. My approximation of f of 1.4 then is 19. So this was 2 points, 1 point for doing your Euler's method with 2 steps, and then 1 point for your final answer that f of 1.4 is approximately 19 or 19.0. All right, let's take a look at the last part. Part D. Part D, write the second degree Taylor polynomial for f. Second degree Taylor polynomial for f about x equals 1. Use the Taylor polynomial to approximate f of 1.4. They are loving this f of 1.4 right now. All right, so second degree Taylor polynomial about x equals 1. That means I need f of 1. Remember our Taylor polynomial formula here. I need the kth derivative of f at a over k factorial times x minus a to the k. In this case, I know my a value is 1, and f is my stuff given. All right, so f of 1, what do I know about f of 1? That's the 0th derivative of f, so just f of 1 is 15. What else do I need now? Now I need f prime of 1. What is f prime of 1? F prime of 1 is 8. Now I need f double prime, someone a little funky, f double prime of 1, because I need the second degree Taylor polynomial, so I need the first 2 derivatives. F double prime of 1, not 2, slow down there, Markwalter. F double prime of 1, I finally get to use this information up here. F double prime of 1 is 20. Now I can write out my second degree Taylor polynomial. You can call it p sub 2 or t sub 2 or whatever. T sub 2 of x is going to be 15 over 0 factorial x minus 1 to the 0 plus 8 over, I'm in my first order now, 1 factorial x minus 1, that's my a value to the k first power because I'm in my first derivative, plus 20 over, I'm in my second derivative now, 2 factorial x minus 1 squared. There is my Taylor polynomial. You don't have to simplify it. It will help, at least just visually though. So 15 divided by 1 times 1 is 15, plus 8 divided by 1 times x minus 1 is 8 times x minus 1, plus 20 divided by 2 factorial is just 2, so that's 10 x minus 1 squared. So there is my Taylor polynomial, my second degree Taylor polynomial. And now I need to use it to approximate f of 1.4. So f of 1.4 is going to be approximately t sub 2 of 1.4, which is 15 plus 8 times 1.4 minus 1. 15 plus 8 times 1.4 minus 1, plus 10 times 1.4 minus 1 squared. All right, because I can just sub in 1.4 for all my x values. All right. You don't need to simplify that. In fact, I encourage you not to simplify for that one. But if you are feeling really, really cheeky, you could say 19.8. All right. Hopefully that gives you some insight. This last problem is 2 parts. 2 points, 1 point for your Taylor polynomial, and then 1 point for your approximation. All right. Please go ahead and check the scoring guides, and make sure you fill out the score report as well. Bye.